Hello, everyone, and welcome to today's graph reading group.
We're joined by Wei Tao, Li Mei, and Yang Shi to present their new 3D graph neural network framework. Let's go.
Yeah, thanks for the invitation, Hannes. So, yeah, we are happy to present here today about our paper, a new perspective on building efficient and expressive 3D eco-aware graph network. So we have three equally contributing authors: Wei Tao, who is a postdoc right now at the University of Chinese Academy of Science, a postdoc there, and I'm a first-year PhD student at Cornell, and Li Mei is a fourth-year PhD student at TMU. We're gonna present this paper today. So yeah, first, I believe everyone is very familiar with this topic, but I'm gonna briefly catch up what is equivariance and why we want it. So a very basic common example for invariance and equivariance is that invariance means when you apply some a group of action, the output remains the same. For example, on this on the left figure where you have a cat inside this image, whether you translate it or not, a convolutional neural net can still tells you there's a cat in it. So the output won't change, it's invariant. And the equivariance is a more general concept where invariance is a specific case of equivariance. For equivariance, if you have a cat and then you translate it and your convolutional layer, because it shares weight around this area, and when you shift the cat, the feature map you're gonna get the cat. It's not a real cat, but the feature representing the cat will also be shifting in the same way. That's called translation equivariance. Okay. And what are 3D covariant GNNs? And yeah, this kind of like define our scope. We are studying 3D Euclidean space graph neural networks, and what kind of actions we are equivariant or invariant to. So yeah, I'm putting several common examples like small molecules, larger biomolecules, crystal structures, point clouds. These are all 3D objects in Euclidean space where requires encoding physical symmetry to reduce degree of freedom, where if you don't encode such symmetry, if you rotate the crystal structure, it won't change its property, for example, conductivity or energy. But other things will change, for example, the force, because force has direction and applies to each atoms. If you rotate the molecule, the force will change equivariantly, just as the cat changed in the previous slides. So what are we going to talk about here today? There are, I think, three types of actions we are considering. First is permutation, where for graph or set object, if you permute the order, the node representation of the graph you're going to learn will be permuted in the same way. Or we call it permutation invariant. If you want to predict something, you have a pooling, some pooling or mean pooling, which ignores the orders of your input, where you always get the same answer. But here it has been very well studied in the past for permutation invariant and for graph neural network. So we are going to focus on things in 3D, E3 or SE3, Euclidean 3 or special Euclidean 3 group. So the difference between these two groups is that E3 includes reflection, but SE3 does not include reflection. It only includes translation and rotation. This is not this is not something we need to specify for now, but for certain cases, there are always some properties that are sensitive to reflection, but some are not. For example, the energy of a molecule is not sensitive to reflection at all, but some properties of molecules might be sensitive to chirality, which is just a reflection. Or for example, if you want to generate some molecule, if you generate like the left hand or right hand, it will be either toxin or medicine. So yeah. And of course, yeah, 3D covariant GNNs are very, very popular. Has been developed. A lot of efforts have been made in the past, I would say 3-4 years. Yeah, maybe more, but more popular by today. So here are some of the very representative examples we're showing, and they are achieving equivariance different ways. We are going to talk about in the following slides, but just show, yeah, they're popular, and also there are some ways to wield them systematically. And following the very general graph neural network or message passing neural network like scheme, we usually talk about 2 parts or 3 parts, but we put 2 parts here. First part is how do you aggregate information from a neighbor? What information you're aggregating? Message calculation, where you have I denotes a nodes, and the J is the neighbors of node I, where you're aggregating your neighbor's information. H denotes some features where you can specify. And E is the edge between I and J. It could be features. And then you have a message function, IJ. And then you calculate this function and you have aggregation. You're going to aggregate your information from a neighbor, usually sum pooling or mean pooling. And then you're going to have a update function where you're going to, it could be simply a multi-layer perceptron to parameterize your message and update. Yeah, these are, I believe you guys are very familiar with these. So yeah, how do we implement 3D covariant GNNs and what we need to consider? So there are many geometric quantities where here we specifically talk about scalar. Scalar is very common. It's like energy, like some prediction tasks like inductivity and just the one dimension which has no direction. It's type 0 is always scalar value. And there's a vector. Vectors are also very common. You get a position where it's 3-dimensional, it has direction, and then you got a force applied to each of the atom. I see a question there. Yeah, please. Okay, right, there's a review, I think. Yeah, of course, yeah, there's several good reviews, such as the Geometric Deep Learning book. And there are also higher order tensors which are not that common. It's very common in real life, but we probably do not realize all the time. So there's stress in fluid dynamics. And yeah, it's very general. It could be arbitrary order. And the first way, I think the one of the very common way, especially in the early days when developing 3D GNNs, is called scalarization, where because scalar value, it doesn't have direction because you can do whatever on it. You can do any nonlinearity multiplication on it. It won't change anything because it's just scalar. It doesn't have any direction. But for vector or tensor quantity, you need to handle them carefully. You cannot just do nonlinearity or multiplication on it. You can only do summation and subtraction. So one way to handle them is that, okay, can we scalarize those quantities hopefully without losing any information about their higher order? And one common way is, we'll talk about another way later in the next 2 slides, but the very simple way is to just explicitly fit those in pairwise distance, because we have the Cartesian coordinates. We can calculate the distance between each pair of nodes, and it becomes a distance where it doesn't have any direction. It's a scalar. And you can also calculate, we all know angles or dihedral angles are important for many of the molecule-related tasks. And you can also encode those features. You just extract them and encode them as features, as they are invariant, so you don't need to worry about. So
Ernest has a question.
There's a question?
No, I was just raising my hand. Yeah, I want to say, can we maybe look at the next slide, like because we're on the I guess now this is less of an overview, right? Because we're in the learning on graphs and geometry reading group. We're, I think, also familiar with concepts like equivariance and so on. But here, I guess, we all know things like EGNN, PAIN, GPP, but I guess it won't hurt to go over over your tensor representations.
Yeah. So yeah, I can do. Yeah, it could be very brief. So there's not. Yeah, prefix space is very simple and efficient, but of course it requires you explicitly encode those things. But actually, these things can be encoded automatically or inherently. Where the second way is another very popular way to use equivalent representation operation, such as tensor, like tensor product, where it guarantees equivalence. For example, using spherical harmonics and the CG decomposition, which leverage irreducible representation such as tensor field network, ST3 transformer, ecoformer, and we are citing another paper here. This paper basically proves, it's a theory paper. It proves that you do not necessarily need spherical harmonics plus CG decomposition. You can use pure tensor product, and it's also going to be universal approximator. The GNNs you are building can also approximate any continuous equivalent function. So here we are talking about, we'll explain the details later, but why we put the EGM, PAIN, GVP in others, because we are talking about expressiveness, where if you can encode any continuous equivalent function, this will be introduced later, but we are showing two ways people define theoretically can achieve such property, right? And I think Victor, you can take it away about frame.
Okay, so I will continue with this slides. So basically, I will introduce a scalarization technique that is motivated from differential geometry. So this scalarization provides us a systematic way to transform equivalent quantities to scalars. So basically, we need to introduce a new concept called the frame bundle. So frame bundle is to assign. Suppose you have a discrete manifold, and at each point, you have a tangent space that represent the local directions around this point. So at this tangent space, it's a linear space, and for linear space, you have frames like a vector basis that can express the, if you live in a three-dimensional space, you have three directions. So the frame is consists of three vectors, and so the frame bundle is a collection of all the possible frames. And once we have a frame bundle, we can lift a equivalent function on the manifold to a scalarized function on the frame bundle, because for equivalent function like a vector field, you can always express this vector in any frames. So like for example, if you have two frames, it's like two observers. Two different observers, and for each observer, you project a tensor quantity into the frame. Then you have like many tables of numbers, and you collect all the numbers. You have a scalarized function on the frame bundle. So the nice thing about frame bundle is that any covariant operations on the manifold can be scalarized. For example, covariance derivative on the manifold it's just a normal directional derivative on the frame bundle. So this technique can be applied for equivalent GNNs. For example, the Lie transformer. No. Still that page. Yeah, the Lie transformer architecture leaves the inputs to the Lie group of orthogonal transformations. And for the frame bundle, like for every 2 frames, you can connect them with an orthogonal transformation. So it's equivalent to leave to the frame bundle is equivalent to leave to the SOD group. But one thing, very difficult thing for realizing this is that there are infinitely many frames. So for practical calculation, you can only approximate them, like sample many frames and do the average. But this is just an approximation. So we improve this by introducing an equivariant frame. Okay, next page. So equivariant frame is a special frame that consists of 3 equivariant vectors. And by taking inner product with equivariant vectors, you have invariant scalars. For example, an equivariant vector can be projected into this frame. And also for higher order tensors, you can take the tensor product of the equivariant frame and forms a frame on the higher order tensor space. Then you can project them on that basis, and you have a type of scalars. So through this scalarization by equivariant frame method, there are 2 benefits. The first one is there is no information loss because this transformation is invertible. So for example, if you have 3 scalars, then you pair them with the equivariant frame, you get back to the same equivariant vector. And the second is once you have performed scalarization, so you can apply any nonlinearity because they are just scalars, and the nonlinearity won't break the symmetry. Yeah, next page. So we have this community graph. Like on the top, it's an equivariant function we try to learn. So the first step is you can do the scalarize the input, and for the output you also do the scalarize. So after this 2 scalarization, you arrive at the bottom line of this diagram. That is the input is scalars and the output is also scalars, and the equivariant function becomes an invariant function. So for invariant functions, you can just use any ordinary graph neural networks. Okay, next page. Right, but there is one thing that it's worth discussing, because we empirically found that on the CloudNet, we found that if we squarize the 3D point cloud by edgewise frames, it's better than the node frames, and the node frame is better than the just scalarize everything by a single global frame. So this motivates us to build a
Oops, did he just disconnect?
Yeah. Lagrangian based on local scalarization. And this, sorry, I get there. Okay.
Vital?
Hi.
Yeah.
We're back. Yeah.
You were disconnected briefly here, but I think.
Okay.
Mm-hmm. I think you can continue with, you weren't disconnected for a long time. And I think you can continue with explaining the message update.
Okay, okay. So this motivates us to, the standard pipeline of GNN is a message passing framework that is aggregated local message to express global quantities, right? So this motivates us to study one-hop-based equivalent 3D GNNs, and especially we want to analyze like what geometric information we can encode by local scalarization or local equivalent message, and what geometric information can be obtained by aggregating these local geometric messages. Right. So this page also lists the formulas for the message passing. Yeah. Okay, so for the local geometric message, so to analyze the expressiveness power of local message, we define a hierarchy of local SE3 isomorphism. So this is inspired by last year's SAR paper on the expressing power of 2D GNNs. That is, you don't have 3D coordinates on each node. So that is the left figure on this slide. So I will briefly mention what the message in this paper. Basically, they built a connection on one WR test. That is, build a connection on the one WR test and the one-hop-based message passing GNNs. For example, they prove that GNN is as powerful as one WR test if and only if they map non-isomorphic subtrace in the graph to different embeddings. So, for example, the SV1, SV2, SV3, SV4 in this figure, they share the same subtree structure because it's all of the star shape. But they are different because beside these star shape, they have different edges connecting the one hop neighbors. But for one WI test, all GNNs as powerful as one WI test, they can only differentiate subtree structures. And so for them, the SV1, SV2, SV3, and SV4 are all the same. So one way to improve this is to introduce structural coefficients that is based on the overlap subgraph. For example, the SV2, if you look at the edge connecting V2 to the right node, so this subgraph, they have a common edge connecting the top node to the right node. But for SV1, they don't have this edge. And for SV3, not only the edge connecting V3 to the right have this edge, but also the bottom edge. Yeah. So from this overlap subgraph, they are different. Okay, so for the 3D structures, we can define a similar kind of subgraph isomorphism. So we name it as a tree, local tree isomorphic triangular isomorphic and subgraph isomorphic. I won't tell you the formal definitions because the notations is heavy, but if you can see the example in this graph. So for the left, you can see if you look at this edge from connecting xi to xq, this subgraph contain two triangles, like the IPQ triangle and the IQM triangle. And for the SJ, if you look at the edge connecting G to Q, it also this overlap subgraph also contains two triangles, but the the relative angle between these two triangles, that is the how to say there. Yeah, the relative angle, like it's different. So in terms of the triangle isomorphism, these two graphs are not isomorphic, but they are isomorphic in terms of local trace because the distance of IP, IQ, and IM are the same with JP, JQ, and GM. Yeah. The right figure shows an example on the, like they share the same triangular structure, but different subgraph structure, because there is no edge connecting P and I. So if you look at the edge of PI, this overlap subgraph only contains one triangle, that is the QPI. And for the edge IL, there is also only one triangle. So if you look at these two isolated triangles, they are the same with the right side. But if you look at these two triangles as a unity, then they are not the same, because the distance between P and I and the distance between the P and I on the right is not the same. Yeah, so based on this, we can improve the expressing the power of equivariant GN by introducing equivariant structure coefficients that take the the period. Yeah, this one. Next page. Right, the AIJ, it takes the overlap subgraph, HVS overlap subgraph as inputs and outputs a number. If this number is is injective on the over the local overlap subgraph, then this number tells you the structure difference between the local geometric shapes, and we can prove that there exists such mapping because locally you have local injectivity, either by scalarization through HVS frames or by equivariant method like the ACE, the atomic cluster expansion, because they form how to say a complete basis inside the function space of continuous functions. So like you can always find you can always express and find a continuous function that can tell the structure difference. Yeah. Next page. We can skip this one. All right. So after analyzing the expressiveness power of local message, we analyze how they aggregate, and a natural question is whether all the environment information can be obtained by just aggregating local environment informations. This is a natural question because we have shown earlier that on the local level, all geometric information can be expressed as invariant scalars by scalarization and tensorization. But we show that, for example, if you look at this graph and you want to express an invariant function that depends on the cluster B and the cluster C. And we can find examples that, for example, if you take the tensor product of vectors inside cluster B and vectors inside cluster C, and you take the norm, then you cannot express. This is an invariant function, but you cannot express them as local invariant scalars inside cluster B and the union of scalars inside cluster B and cluster C. The reason is that you miss the information of we call the frame transition. So frame transition also comes from the scalarization by frame method. Because we do local scalarization, so inside cluster B we use a local frame, and inside cluster C we use another local frame. But you don't know the relative orientation between the frame B and the frame C. So this information cannot be, because it's a interrelation between B and C. It cannot be expressed by scalars inside B and inside C. You can only explicitly encode them in the message passing scheme. And if you introduce them, then you can express anything. That's what we prove. Yeah, next page. Oh, yes, and this is a neural shift interpretation of our method. So the neural shift diffusion is a kind of a unified framework for 2D GNNs. But for the 3D GNN, you also have a shift because, as we have mentioned earlier, the scalarization method comes from scalarization on the frame bundle. So frame bundle itself is a shift. So basically, we can build a shift based on the frames. For example, recall the definition of shift. That is, you have 3 components. One component is you have a vector space for each node on the graph, and you have a vector space for each edge on the graph, and you have a restriction map that maps vectors of each node to the edges and connect this node. So in our framework, there is the natural linear map, restriction map, because we have edge frame and we have node frame. And so the linear map is exactly the linear the linear transformation between these two frames. And the vector space is just the equivalent vectors of on each node. Okay, following this, you can define the Schiff Laplacian. That is the key component for performing the message passing. And in our case, we can write the explicit formula for the Schiff Laplacian, and we found out that the FV transpose times FU equals the FTE information we defined earlier. Yes, that's all for our method.
All right. I think that's a pretty clear presentation of the method. And now?
So that's
well, I'm just wondering if you still want to say something next, like this Schiff interpretation, or yeah, what's going on? So are we done with the presentation?
Not yet.
All right, then who's continuing?
Hi, Yuanqi. You can continue on this slide.
Yes. So I wonder if Wei-Tao was just stopped and asked whether there are any questions, I guess. But yeah, okay. Yeah, if there's no question. So yeah, there's implementation of LeftNet basically following what we discussed before, where wait, let me bring up the cursor. Yeah, so we have input 3D graph where we go through the embeddings and the interactions. And we also pre-process kind of like the input 3D graph to construct the frames mentioned before, and build the subgraph, extract the information from the subgraph, map onto the frame as our local structure encoding. Yeah, more explicit here, where you got this edge frame and this local structure isomorphism mentioned, and you map them on the graphs. You only pre-process them once. So we still consider us as one hop message passing rather than actively, iteratively message between those neighbors, which I think usually called two hop message passing. Yeah, and these are the details, explanation about how things work inside. And we also have a pseudocode in the paper, so we won't go to details. And then it comes some experiments. So we conduct experiments on two popular data sets, QM9 and MD17. Here, so QM9 is a predicting quantum mechanical properties of small molecules, where all the properties are scalars, where we compare with kind of like previous state-of-the-art method, and the results, yeah, we kind of like comparative or outperform them without much parameter tuning, because yeah. And also MD17 is a kind of machine learning force field data set which has 8 tasks to predicting the force per atom and the energy. So here we also compare with those previous method and showed the results here. Note that there is a revised MD17 version. We put the results in our appendix, stress of the previous reviewers, which MD17 has some errors in it, I think, and they have a revised version. Yeah. So yeah, as the other 3D GNNs or this framework, we believe that it has broad applications in many modeling all kinds of 3D objects, because this ideas of frame is from differential geometry, and this is general. Yeah, at least as general as previous method. And there are any kind of task involving 3D objects. Actually, we've been also testing on generative task. We've tested other methods as well. Personally, we would say our method is very effective on the task we've been testing. Yeah, that's the application. And so regarding the code, we are going to because we are still developing a kind of like a newer and more efficient version of this, because right now, so we're gonna release code very soon, and we hope this we hope this will be used by the community. And if anyone has any feedback or questions, we are happy to answer.
Yeah, maybe why do you think is this? Why should I be excited about this new 3D network instead of, I don't know, the new work from Alexandre Duval with the stochastic frame averaging, or all these million other 3D GNNs? Yeah,
we could give some brief. We haven't discussed them in our paper, but we haven't discussed that new work yet because it just released. We did have a very brief look through over it. I think it shared a similar concept to use frames. They followed a previous work called frame averaging, where they built the global frame, as we mentioned. But as we tested, because we are basically presenting two works today. First is ClothNet. First use what we call local frames to construct IC3 equivariant graph neural network. And the second work is what we call a new perspective to discuss the two expressivity. One is on the geometry and one is on the frame aggregation expressiveness. So I think we have tested our first work, ClothNet. It was published in 2022, where, I think Weitao briefly mentioned that we found global frame was not as good as edge frame, but we were quite interested in how because their method worked quite well. So we are interested in, we'll look further on that. We also maybe go back to test global frame. The framework not constructed in the same way, but it has some similar ideas in it. That's the stochastic frame averaging framework. For the others, I think as an alternative to, Weitao, do you want to add something? So I think in terms of expressiveness, we have figured here, because we mentioned that those methods based on spherical harmonics and the reducible representation, they are also very expressive in terms of approximating continuous equivariant function. But the extra benefit of method is we introduce this local structure encoding, where I don't think they have discussed in their paper. If you want to compare with them, because if you see this table for ecoformer, the FT frame transition encoding, they're almost check mark, but they didn't discuss anything about the local structure where we come from, local graph isomorphism.
Nice.
How about the generative model goes back to the original space? So I think again, briefly, because we also work on general model. So we are still dealing with, we use the frame to scalarize the vectors. I think as Weitao mentioned here, a benefit of this method where when we initially propose it is that, theoretically there's no information loss, because your operation is invertible, where you scalarize your tensor, and based on this equivariant frame, you can tensorize it back. But there are also some recent awesome work from Tomi's group, I think, also diffuse over the frame. over SO3. Yeah, but yeah, essentially we are not mapping onto another space. And yeah, if this is considered a mapping, is invertible. So we just aggregate the message there, but we can also keep another like a tensor or vector where we could also update them. We are aggregating information in this way, but we could also keep separate the scalar, vector, tensor output and update all of them. If that answers the question. Yeah.
Okay. Yeah, nice. Thanks for that explanation, and thanks, Francesco, for the question. And yeah, do we have any other questions, or how do we want to proceed? I don't think there's anything coming up, but if you no, Denise.
Yeah, I can probably ask a question, but this probably will be a little bit of a noobish one because I'm a novice in this field. But this AIJ term was used to actually transition to this equivariant state, and you say that it can be computed only once before actually running the network. I'm just a bit lost if it is computed specifically for graphs in the training set, or it can be generalized on like any graph. So yeah, I see that this is obviously like structure specific. So it seems like each edge has its own parameter, right?
Yeah, I think empirically, once we construct the edge frame, and we know the neighbor, we can just map those the neighbors of the node I, like node J, onto that frame. Yeah, I think technically it could be computed for any graph, but we need to build the frame.
I think this frame can be computed for any like 3D point cloud, because we only use the positions of xi and xj. So if you look at the 3 points, like the first point is the center of mass of this system, and the other 2 points is the xi and xj. So it will form a plane, and the third direction of this frame is just the normal direction of this plane. So it will form a frame for every 3D point cloud.
Yeah,
and every edge.
Yeah, side note to this, we probably didn't mention enough, is that, for example, work like EGN, they leverage only this relative direction between node I and J, where we have a complete basis where you're not only having this one direction, but you also have we construct a frame where it has 3 directions, which is complete, which was also what we prove universal approximation based off with the scalar. Yeah, that was some details. Yeah, it has 3 directions.
I see. So, okay, I think you answered my question well. I just wanted to ask, theoretically, this cannot be further, like, this will be much harder to maybe generalize further for the fourth dimension. So it is specifically designed for the 3-dimensional case of the graph, not the like arbitrary, obviously dimensional. So I mean, you said that you can go from the 2-dimensional case to the 3-dimensional case with this Schiff generalization, but I guess for the next dimension, it can be applied the same way.
Yeah, I guess we told me how better answer. I think the question is, can we generalize to higher dimension than 3?
Not to the arbitrary, but just one more.
Oh yeah,
is it
like
theoretically possible?
Yeah.
Yeah, like in the higher space, you need more points to build a frame. If you like for an edge, you cannot just only use 2 points to build a frame for higher dimensional space. You need more points.
Yes.
But, yeah.
So the problem here is that okay, this I understand, but I don't quite follow. If you have a graph in the four-dimensional graph, then in the four-dimensional world, then wouldn't you have extra points as well? Okay, sorry, I guess that maybe this is a pointless question because I have not thoroughly investigated this field yet. Yeah, anyway, thanks for the first question. Thank you.
Yeah, thanks. I believe there's a kind of like internet because Weitao is in China, missing. Yeah, but I think Weitao's answer is quite yes, but you need some special, and it may have problem with scalability because you need more reference to build frames, things like that. But yeah, of course we could discuss more offline, right? So, Weitao, I think there's another hand raised about do you use the frame change in the message passing? This FTF term?
Yes. There are 2 ways to realize this frame change. The first way is to introduce equivariant message into the framework. Like you can, like for each edge you have an edge frame, and if you equivariant algorithm, then you can, and after aggregation, you do a equivariant update. You can implicitly calculate the frame transition information. And the second way is to, the second way is the neural shift. Like if you use node frame, then you can you can calculate the frame change between the 2 node frames, and you can build them as an edge-wise feature. Yeah, like this formula.
So it will be an alternative way, if I understand correctly.
Yeah.
I see. Thank you. I have a question about the local framework. How do you disambiguate equivalent local frames?
Sorry, I can't hear you clearly.
Yes. How I suppose that there could be multiple local framework, no? A frame. How do you choose in a unique way the local frame? Because the distance is given, but
yeah, I know your question. Because we define a hierarchy of 3D isomorphism, and the key point is the edgewise overlap subgraph, and because it's an edgewise overlap subgraph, it's like you can do you can express them by edgewise equivalent frame, and for edgewise equivalent frame, you don't have much choice because you only have 2 nodes, and for these 2 nodes, there is no. I think maybe there is not much choice for you to build an equivalent frame only based on these two nodes.
Yeah. I think the answer is the way we build frame is very specific and unique, like over the.
I won't say it's unique, but yeah. But you don't have much choice because you only have 2 points.
Okay, thank you.
Okay, now we understand this 3D GNN as well, and we'll maybe discuss some more here in the reading group. So if you don't want to miss that, then join us with all the information down in the description. See you around.